Hello everyone, thanks for watching Edupedia World videos. So continuing with chemical equilibrium, today we are going to look at the effect of temperature on a system present at equilibrium. Okay, we'll try and use Le-Chatelier's principle, or maybe we'll use a mathematical way to see the effect of temperature. Okay, so let's see. The statement goes as follows, that the temperature, okay, how it affects an equilibrium basically depends on something called heat of reaction, okay, or heat of reaction at constant pressure, which will be delta H. All right, so the change in temperature shifts the reaction in accordance to the value of enthalpy of your reaction or the heat of your reaction. Okay, so for example, if delta H is greater than 0, it will shift in a particular direction. If delta H is less than 0, then another direction, and if delta H is equal to 0, then maybe something else will happen. So the dependence of temperature on a chemical equilibrium or even on a physical equilibrium will depend simply on the value of delta H. Okay, so in a few minutes we'll look at the details of the delta H. So temperature changes the K equilibrium value itself. Okay, so until now all the effects that we studied, effects of pressure, volume, concentration, or even catalyst or inert gas addition, so in all those cases we saw that the equilibrium constant value, K equilibrium value, remains unchanged. Okay, it is not dependent on any of those things, and the only thing that used to change was the reaction quotient. As a result of this, the equilibrium shifts in a direction so as to make Q once again equal to K equilibrium. This time, because equilibrium constant value for a given reaction depends on temperature, if we change the temperature T itself, then the value of K equilibrium will change, while the value of Q, reaction quotient, at that moment remains same. Okay, so now once again the reaction will shift in a particular direction, whether forward or backward, so as to make the Q once again equal to the K equilibrium, but this time a new value of K equilibrium, let's say KEQ prime. Alright, so just remember, this is an important point, that temperature will change the value of equilibrium constant itself to a new value, and that is why the reaction shifts in a particular direction, so that Q will have to change to once again become equal to K equilibrium, a new value of K equilibrium. Okay, so now let's look at the meaning of delta H. Okay, though we'll study it in detail in thermodynamics, here we'll just look at a rudimentary way of understanding the value or the meaning of delta H. So all the processes can be divided into endothermic or exothermic, or maybe some which are neither of them. Okay, so what is an endothermic process or an endothermic chemical reaction? Okay, so it is a process in which energy is essentially absorbed by the system. For example, if I have A, all right, and on this A, okay, I am supplying heat. All right, so if I supply heat to this A, it will absorb this energy, and upon absorbing this energy it changes to, say, another substance called B. Okay, so in this process where A absorbed energy to change itself to B, this entire process required supplying of energy. Okay, or this is a process in which the energy was absorbed by the system, so this becomes your endothermic process. There are several examples of such kind of process in the world. Okay, pretty much everything requires energy, so when you supply energy, that process becomes an endothermic process. Example, when you supply heat to cold water, it becomes warm. When you supply more heat to a warm water, it starts to boil. So all these are examples of endothermic process. Okay, for example, if you have ice, solid ice, all right, if you supply heat to it, okay, if it takes heat, that means if it takes energy from the surrounding, it is absorbing heat, and in this absorbing heat it changes itself into liquid water, it melts. Okay, so even melting of ice is an example of endothermic process. Okay. So for such processes which absorb heat or energy, the value of delta H is said to be greater than 0. Okay, that is, in this process, delta H, that is the final enthalpy of your system minus the initial enthalpy of your system, is going to be greater than 0. That is, final enthalpy of your system is greater than initial enthalpy or heat of your system, which is quite understandable because energy is being absorbed, so enthalpy of system will probably increase, and hence final enthalpy is more than the initial enthalpy or heat contained. Okay, so this is one way to look at it. Once again, we will study this in greater detail in the chapter of thermodynamics, but for now we are just trying to assimilate whatever we can to understand the effect of temperature on equilibrium processes. So endothermic processes are the ones for which delta H is greater than 0. For example, breaking of bonds. So when you have any kind of physical or chemical association between two molecules, atoms or ions, basically any entity or species. Alright, so when you break this bond or when you pull them away, okay, this process is always essentially endothermic in nature. That is, it requires energy. Okay. For example, if you have say a bond between H and Cl, which is a covalent bond, if you want to break this bond so that H and Cl can separate from one another, you need to supply energy over here, and hence breaking of bond is always, without exception, an endothermic process. Okay, here you have an ionic bond which you need to break so that the ions Na positive and Cl negative can separate out and stay away from one another. So once again, this is an endothermic process. Okay, there are many more examples which we don't have to go into right now. Likewise, there is something called exothermic process. Okay, so exothermic process is just opposite of endothermic process. It is a process in which energy is essentially released. Okay. So for example, if I have B in the previous example, alright, if I had the substance B, when substance B releases heat or energy, okay, when it releases energy to the surroundings, okay, it changes itself to another substance A. So this process in which B changes to A, okay, was accompanied by release of energy to the surroundings from our system, and hence it is an example of exothermic process. Okay. So for exothermic process, it turns out that delta H is always less than 0. That is, H final minus H initial is always less than 0, which means that the final enthalpy of your system is less than initial enthalpy of your system, which is quite expected because the energy is being released by the system, and hence it will obviously stay at a lower value of energy than it was initially present at. Okay. So that is why delta H is less than 0 for exothermic processes. Okay. An example of this kind can be just the opposite process of melting, that is freezing. Okay, so when liquid water turns to ice, how does that happen? You take your water in a container, okay, and you keep it in the refrigerator. So what this refrigerator does, it cools down your liquid. How does it does that? How does it do that? It absorbs heat from your liquid. The refrigerator takes the heat, okay, and because of that the liquid cools down and solidifies into ice. Okay, so it is an example of exothermic process, that is a process where your system, which is the liquid water, was releasing heat or losing energy. All right, a very common example of exothermic process is formation of bonds, okay, or formation of any kind of physical or chemical association. For example, if I have Na positive here and Cl negative here, separated by an infinite distance, now when I bring them closer to one another, okay, to end up forming an ionic bond, this process will essentially release some energy to the surrounding. Okay, so this is an exothermic process. Likewise, if you form any other kind of bond, let's say between atoms present in the molecule of water, Okay, so here when one H reacts with oxygen to form a bond between H and O, a covalent bond, this formation of bond must have taken place by releasing energy to the surrounding. Similarly over here, so formation of bonds without exception is always an exothermic process, whereas breaking of bond was always an endothermic process. Okay, so this is how the value of delta H determines whether the energy is going to be released in this process or whether is it going to be absorbed in the process. So when we take a chemical reaction which is reversible in nature, a chemical reaction which is reversible in nature, how does it look like? We will have reactants, okay, and these reactants will basically be forming products via a reversible reaction. Okay, so either this reaction is going to be endothermic or exothermic. Which is it? Okay, so when I say that a reversible chemical reaction is, say, exothermic in nature, it means that it is exothermic in the forward direction. That is, when reactants are going to form the products, they are essentially going to release energy to the surrounding. That is, in other words, we can say when reactants change and give us products, they also give us some amount of energy with the products. Okay, so this heat or energy, okay, though heat and energy are different things, we are using them synonymously over here. Okay, once again we'll look at the difference in the chapter of thermodynamics. So here when reactants change into products, it was accompanied by release of heat. Okay, so this is how an exothermic reversible reaction looks like. Okay, so it is going to be exothermic only in forward direction. All right, but when I look at it in the reverse direction, that is in the backward direction, what is happening over here? Okay, the backward direction looks like this, that my products are using some amount of heat or some amount of energy to change themselves into reactants. That is, products are absorbing energy to form the reactants. Hence the reverse reaction or the reverse direction becomes an endothermic process. Okay, so this means a reversible reaction, if exothermic in one direction, it is definitely going to be endothermic in another or the reverse direction. This is always true. Okay, because exo and endo are essentially opposite, so in one of the direction, okay, it is going to be the opposite process, okay, in terms of energy as well. Okay, likewise if I have a endothermic reversible reaction, it means that it is endothermic in forward direction. That is, when reactants form products, they are absorbing heat. Okay, this is what an endothermic reversible reaction will look like. Okay, which also means that in the reverse direction, that is in the backward direction, my products are going to form reactants by releasing some heat, and hence it is exothermic in the reverse direction. Okay, so now we have got a better understanding of the terms endothermic, exothermic, and some more understanding of the value of delta H. So let's look at the effect of temperature on reversible reactions present at equilibrium state. So effect of temperature once again can be understood in two ways, either by increasing the temperature or by decreasing the temperature of a system present at equilibrium. So first let's try to increase the temperature of any reaction present at equilibrium. Okay, so I have reactants on the left hand side and I have products on the right hand side. Okay, so if for this reaction I want to study the effect of temperature, I need to know the value of delta H for this reaction. Is delta H value greater than 0? Is it less than 0? Or is it equal to 0? Okay, so if the delta H value is greater than 0, then for such a reaction, okay, for such a reaction, increasing temperature will shift the reaction in forward direction. Okay, so there will be a forward shift in the reaction. That is, if R and P, that is reactants and products, are right now present at equilibrium, that is rate of forward and backward reactions are equal. Now if I suddenly increase the temperature of this system at equilibrium, what will happen? Okay, my K equilibrium value changes such that the reaction shifts in forward direction, or in other words, the rate of forward reaction becomes greater than the rate of backward reaction because of this increase in temperature, and the system is no longer at equilibrium. Okay, likewise, if delta H is less than 0 for a given reaction, okay, it cannot be both for the same reaction. For one reaction it will either be greater than 0 or less than 0 or equal to 0, not all of them simultaneously. So if for another example, another reaction, delta H turns out to be less than 0, that is, it is an exothermic reaction, then for such an exothermic reaction, increasing temperature at equilibrium will shift the reaction in backward direction, that is, rate of backward reaction will become greater than the rate of forward reaction for such a process. And if delta H is equal to 0, okay, then obviously, since there is no enthalpy change, since there is no heat content change between reactants and products, okay, the temperature is not going to affect the flow of energy or flow of heat, and hence delta H equals to 0 means that effect of temperature will not be there on that system. Okay, so increasing temperature will have no effect on a reaction for which delta H is equal to 0. Likewise, if we decrease the reaction temperature, then all the analysis that we just studied will be opposite. Okay, that is, if temperature is decreased for a system present at equilibrium, and if for such a system delta H is greater than 0, that is, if our process or the reaction is endothermic in nature in forward direction, then decreasing temperature will shift the reaction in backward direction. Okay, so backward direction reaction increases in rate with respect to the forward direction reaction. If delta H is less than 0, okay, for those reactions which are exothermic, delta H is less than 0, and decreasing temperature at equilibrium for such reactions shifts them in forward direction, whereas delta H equals to 0 once again has no effect on the direction of the reaction. Okay, so if delta H is equal to 0, then for such a reaction, change in temperature will have no effect. It will neither shift the reaction in forward nor in backward direction. So why is it so? Why is it that delta H values determine the temperature effect on systems present at equilibrium? So once again, we can look at it in two ways. One of the way is simple mathematical way. In that way, we just need to know the exact dependence of K equilibrium value as a function of temperature. Okay, so what is the equation which determines the value of K equilibrium if I change my value of temperature? So this is something we'll study after 1 or 2 sessions. Okay, so don't worry about it. Mathematically, how do we determine whether the equation is going to shift in forward direction or in backward direction with change in temperature? For now, we'll try and use Le Chatelier's principle to determine the effect of temperature on equilibrium state. So what does Le Chatelier principle say? It says that whenever I make any change to my system at equilibrium, okay, then the system by itself will try to minimize the effect of that change. Okay, so which means if I have a reaction, okay, from in which reactants are going to products, okay, and if I suddenly increase the temperature of this reaction, then system will try to minimize the effect of this increase in temperature. How can it do that? It can minimize the effect of increasing temperature by decreasing the temperature. Okay, so how can a system decrease the temperature by itself? It's pretty simple actually. Okay, either this reaction will be endothermic or exothermic, or it will have delta H value equals to 0. Okay, such processes do not have any specific name, so we can't use that. Okay, so let's assume for now that this process is an endothermic process. That is, here reactants absorb heat to form products. Alright, so for such a process where heat is being absorbed, okay, by the reactants, if I increase the temperature, the system will try to shift the reaction in such a way that it can decrease the temperature again. And how can we decrease the temperature of a body? Okay, temperatures can be decreased by, okay, by getting rid of the heat or by getting rid of energy. Okay, if we take away heat, then temperature decreases. Alright, so that means this system, okay, this system will decrease its temperature by absorbing more and more heat. Okay, if there is excess heat being released, okay, then temperature will obviously increase. It's like putting something on the stove. If you put something on the stove, there is constant supply of heat. Okay, for example, if you take a vessel, okay, a utensil, and you keep that on the gas, all right, then because of constant supply of heat from below, the temperature of this container will obviously increase. Okay, all right, hence if the system wants to decrease the temperature, it will move in a direction where heat is not being released. Okay, so increase in temperature shifts the reaction in forward direction, because in forward direction the system has the capability of absorbing excess heat present and hence reducing the temperature of the whole system. Okay, let's try to understand it again in terms of an exothermic reaction. Okay, so for an exothermic reaction, all right, my reactants are going to form products along with releasing some heat. So for an exothermic reaction, if I increase the temperature, what happens? The system will try to decrease the temperature. And how can it decrease the temperature? By absorbing heat. If there is heat present in your system, okay, if there is heat being released, so how is that heat going to affect the system? It will increase the temperature of the system. Okay, so hence to decrease the temperature, it will absorb heat. Okay, hence increasing temperature for an exothermic reaction shifts it in backward direction. Alright, whereas if you decrease the temperature at equilibrium, then system will minimize the effect of this decrease in temperature. It will minimize this effect by increasing the value of temperature by itself. How can it increase the value of temperature? By releasing more and more heat. If it releases heat, then everything, okay, everything gets heated up, everything absorbs more energy, everything has access to more heat, and hence temperature increases. Hence decrease in temperature at equilibrium, if externally I am decreasing the temperature of my system, for an exothermic reaction, the reaction shifts in the direction where it where it releases heat, that is in forward direction. Alright, whereas if the reaction is neither endothermic nor exothermic, that is there is no net absorption or, okay, supplying or releasing of heat in this process, okay, then even if I change the value of temperature, okay, there is not going to be any effect on the process. Okay, that is your process cannot, okay, your process cannot be affected by the value of temperature, because there is no essential role of heat being played here in this process. Okay, it might have some other role, but not the role of shifting the reaction. All right, so this is what you need to know for the effect of temperature on a chemical reaction. In another session, in the next session, in fact, we'll look at some real life examples in which we'll better understand the effect of temperature, okay, on various industrial processes. So let's take an actual example. Okay, so for this reaction, we have a reactant NO2 forming N2O4 reversibly. So this reaction has a delta H value of around -50 kilojoules. Okay, so this means this reaction is exothermic in nature. Okay, That is, I can also write this reaction as reactants, okay, reactants forming products plus releasing some heat. Okay, it is an example of exothermic process. So if I increase the temperature of this system present at equilibrium, then what will happen? Okay, if I increase the value of temperature for this system, the reaction shifts in the direction where it can minimize the temperature. How can it minimize the temperature? By absorbing excess heat. Okay, so it shifts itself in the backward direction. Okay, it uses up this extra heat, all right, and hence it decreases its temperature. Okay, whereas if I externally forcefully decrease the temperature of this system, since it is an exothermic reaction, decreasing the temperature will shift it in backward direction. That is, now more and more NO2 will get consumed and form N2O4. Okay, that is, rate of forward reaction will have increase and become more than rate of backward reaction, and it will keep on being so until equilibrium is established once more. Okay, in thermodynamics of equilibrium, we will look at the exact dependence of K equilibrium value on temperature. Okay, and based on that we'll be able to determine whether increasing the temperature or decreasing the temperature increases the equilibrium constant or decreases the equilibrium constant, and based on that we'll directly be able to determine whether the reaction is going to shift in forward direction or is it going to shift in backward direction, or is there going to be no effect on the direction of reaction. So until then, and once again, thanks for watching Edupedia World videos.